So next we're going to be running a few more advanced problems on our chip. The first is going to be our sort program. So we're loading in sort.image to context 0 and our end program to context 1. We'll be running it on data 2, which is an unsorted array of the numbers 0 to 31. And we'll be using a data miss rate of 10%. So if you take a look at our program, it looks like this. So first we load in the beginning of the array and the end of the array as constants. And if we start at program counter 4 on the second instruction, the beginning of the array will actually be set to 0. And so we use that to check to either sort the first or the second array using the same sort program. And then from there on out, it's a simple bubble sort program. This outer loop keeps looping until it is finished sorting, and the inner loop is the one that cycles through the array, and if we need to make a swap, it will change the two memory locations here, and then it'll go test if it's the end of the array, and then loop back as needed. So when we actually run this program, it looks something like this. So you can see here are our initial memory values, and they are unsorted. And as we run through them, you can slowly start to see swaps happening. And so this goes on for some length of time. And at the very end of all of it, you can see that we have, in fact, a sorted array. So 31 down to 0. And we can check in on our cycle counter and see that this took us a grand total of 24,941 cycles to complete. Next, we're going to look at running two programs at the same time. So we have our stats program loaded into context 0 and our sort program loaded into context 1. Our stats program is assembled to keep all of the key values that it's looking for in register values. So the sum is held in register 1, the min val and max val are stored in 2 and 3. And so if we look at how that actually runs, you can see that initially we have our first array from 0 to 31 is unsorted, and then our second array starting at 32 is the same thing with its min values at location 3 and its max value of 31 at location 17. And so once we actually run this program, flipping all the way to the end, we can see that it completes in a cool 24,958 cycles, and you can see that the initial array is sorted, and then if we look at the register values, which I've labeled here, we have the sum, the min value, the max value, and the indexes where they were found, and the average.
Alright, in this demo we'll be showing sort, and it'll be running on data, the data.image, which has 32 signed integers in it. So you can see instruction file input 1 is set to sort.image, file input 0 is in.image, and main memory is data.image. Also, the data miss rate is set to 30% right now, and we're using a little trick for the initial program counter is set to 4, so it works on the first 32 words of main memory instead of the second 32 words. So we've already got it compiled, and we'll move over to the waveform and run the wave, and it's done. So we'll switch back to the waveform and hop over to the beginning. So as you can see, it begins in the context 0 and issues the end opcode, and then it switches to context 1 and issues the add opcode and switches back to context 0, and finishes context 0, and now we're going to be in context 1 for the rest of it. And as you can see, the memory is not sorted at all. So now we'll move over to the end, and so now you can see that the context 1 has ended and everything else is done. We've gone through 27,181 cycles, and memory is now sorted. So every so often you can also see that there is actually a memory miss right here. Context 1 memory miss is set to 1, and it's going to stay set to 1 for a full 5 cycles there. Then it's released, and the memory miss is over.
And finally, the work breakdown was this. The instruct and fetch stage was written by Austin, the decode by David, the execute by Austin, the memory by David, the write back by Michael. David wrote the initial assembler, the stall design and data control hazards were done by Austin. Michael handled the memory stalls. David did a lot of the cleanup and organization of all the code, and all of us collectively debugged and tested the chip. For a completely unscientific look at how the work was distributed, according to the subversion tool Blame, it broke down pretty evenly with each of us writing over 1,000 lines of code.